Dear students, in this class, we'll discuss about the deduction of gas laws from kinetic gas equation. So, how to deduct the different gas laws from the kinetic gas equation. So, we know that the kinetic gas equation PV is equal to 1 by 3 mnc square. So, how to deduce the Boyle's law from the kinetic gas equation? So, according to the kinetic gas equation, if you are removing or reducing Boyle's law, PV is equal to 1 by 3 mn c square. That is kinetic gas equation. So that 1 by 3, I am writing it as 2 by 3 into half mn c square. We know that half mn c square is nothing but Ke. So we are writing it as PV is equal to 2 by 3 Ke. So according to this, Ke is equal to Kt. So PV is equal to 2 by 3 Ke. Instead of Ke, we are writing it as Kt. So that is nothing but temperature is constant, PV becomes constant. So PV is equal to constant. So that is Boyle's law. So we are deducing Boyle's law from kinetic gas equation. Next one, Charles' law. At constant pressure, V is directly proportional to T. We have to prove that V is directly proportional to T using kinetic gas equation. That is PV is equal to 1 by 3 mn c square. So this 1 by 3, and further I am writing it as 2 by 3 into half mn c square or 2 by 3 Ke. So PV is equal to 2 by 3, Ke means Kt. So PV is equal to 2 by 3 Kt. So if you bring V is equal to 2 by 3 Kt by P. According to the Charles law, pressure is constant. So 2 by 3 K by P. So V is directly proportional to T. So because temperature is V is directly proportional to T and pressure becomes constant. So V is directly proportional to T. Next one, Dalton's law of partial pressure. So at constant temperature and volume, so we have to show that P is equal to P1 plus P2, where P is the total pressure and P1 and P2 are the individual pressures or partial pressures. Suppose N1 molecules of gas I, each of mass M1 and RMS speed C1 occupy at a volume. The pressure P1 of the gas is given by P1 is equal to M1 N1 C1 square by 3V. So Dalton's law, second molecule. So P2 is equal to M2 N2 C2 square by 3V. So total pressure if you take, so P is equal to P1 plus P2, that is M1 N1 C1 square by 3V plus M2 N2 C2 square by 3V. So P is equal to P1 plus P2. So that is Dalton's law of partial pressure. Now coming to Graham's law of diffusion, we have to prove that R is proportional to 1 by root D. So according to the kinetic gas equation, PV is equal to 1 by 3 Mn C square. So small m and small n, I am writing it as capital M. That is nothing but capital M is molar mass. So PV is equal to 1 by 3 mc square. So C square is equal to 3 PV by m. So we know that density is equal to mass per volume. Here volume by mass. So volume by mass is nothing but 1 by D. So C is equal to root of 3P by D. Because pressure is constant, C is proportional to 1 by root D. C is nothing but RMS velocity. R is nothing but rate of diffusion. So R is proportional to, since C is directly proportional to R, instead of C we can write it as R is directly proportional to 1 by root D. So next one, Maxwell distribution of molecular velocity. So how the molecular velocities of gas molecules distribute. So Maxwell Boltzmann distribution of speeds. So we know that the gas molecules are separated by large empty masses and moving. All the gas molecules will be moving rapidly and randomly in all the directions. So while they are moving randomly and irregularly in all the directions, so they collide with each other and also with the walls of the container. So what will be happening, since they are undergoing different types of collisions, the speeds and the directions of the molecules keep on going or changing. So they do not have the same speed. So they will be, the speeds will be varying. So on the basis of these factors, that the speed will be constantly changing, the Boltzmann proposed that it is not possible to find out the speeds of individual molecules at from the probability consideration. It is possible by distribution of molecules among different speeds. This distribution is known as Maxwell Boltzmann distribution. So if you see the graphs, so the distribution curves remains constant at particular temperature. So if you see the graph between the fraction of molecules and speeds, so see most the highest graph, that is most probable velocity, and second one is average velocity, and third one is RMS velocity. So what are the conclusions that we can draw from the Maxwell Boltzmann distribution of speeds? So the fraction of molecules with very low or very high velocities is very small. So that means the fraction of molecules which are moving with very low velocity or which are moving with very high velocity will be very small among the total number of molecules. So the fraction of molecules possessing higher speed goes on increasing till it reaches the peak. So that means till it reaches the peak, it will be increasing, continuously increasing after reaching the peak, and thereafter decreasing. So the maximum fraction of molecules possessing a velocity corresponding to the peak of the curve. So that molecules is nothing but most velocity is known as most probable velocity. So if you see the definition of most probable velocity, the velocity that is possessed by the maximum number of molecules at a particular temperature. Suppose if you are considering 100 molecules, of that 100 molecules, if 70 molecules or 80 molecules are possessing one kind of velocity, that velocity is known as most probable velocity. So if you see the effect of temperature on the distribution of speeds, on increasing the temperature of the gas, the molecular motion also becomes rapid and the value increases. Then the entire distribution curve shifts towards right as the temperature increases. So as the temperature increases, the fraction of molecules having higher speed also increases. So see, this is the graph, the fraction of molecules and molecular speeds. So as the fraction of molecules, molecular speed increases, the fraction of molecules also increases. So here we can see at different temperatures. So next we'll see about the molecular velocities. So what are the different types of molecular velocities? So the gas molecules move irregularly in all the directions, we know that. So there are moving with different types of molecular velocities. So the molecular velocities, what are the different types of molecular velocities? Most probable velocity, average velocity, and RMS velocity. That root mean square velocity. When we are considering root mean square, so if V1, V2, V3 are the velocities of different molecules, then the total kinetic energy of n molecules is the sum of kinetic energies, and V is the velocity that is possessed by each molecule. So total K is equal to n into half mv square. Then K is equal to n into half mv1 square plus half mv2 square and v3 square and so on. So that is equal to half into m into n into v square. That is equal to half m v1 square plus half m v2 square plus half m v3 square and so on. So ultimately RMS velocity is equal to root of V1 square plus V2 square plus V3 square by capital N, where N represents the number of molecules. So if you see RMS velocity, so we can calculate the RMS velocity at different conditions. When temperature is given, RMS velocity is equal to root of 3RT by M. That is equal to, we know that PV is equal to RT. So instead of RT, we can substitute PV. So is equal to root of 3PV by M. So that is equal to root of 3PV by M. So where P and V are volumes. So we know that V by M density is equal to mass per volume. Here V by M is there, that means 1 by D. So that is equal to root of 3P by D, and that can be equated to root of 3 HDG, because P is equal to HDG. So HDG by D, where D is the density of gas and D is the density of mercury. So next one, average velocity and most probable velocity. So average velocity or average speed. It is the average of the velocities of different molecules at any instant at a given temperature. So if V1 and V2 and V3 are the velocities of different molecules, average velocity is equal to V1 plus V2 plus V3 by capital N, where N is the number of molecules. So here also we can calculate the average velocity at different conditions. When temperature is given, average velocity is equal to root of 8 RT by pi m. So instead of RT we can substitute PV. So 8 PV by pi m is equal to root of 8 P by pi d, or is equal to root of 8 HDG by pi d. So these are the different conditions: temperature condition, pressure and volume condition, density condition. So if RMS velocity is known, if RMS velocity is known, we can directly calculate the average velocity, that is equal to 0.9214 into RMS velocity. But the condition is we have to know the RMS velocity. Then only we can directly find out the average velocity. So next, most probable velocity. So already we have discussed, it is the velocity or the speed possessed by the maximum fraction of molecules. So most probable velocity is equal to root of 2 RT by m, or is equal to root of 2 PV by m, is equal to root of 2 P by D. So these are the most probable velocity at different conditions. So that is temperature, pressure and volume, and density. So if we know the RMS velocity, we can directly find out the average velocity, that is equal to most probable velocity, that is equal to 0.8166 into RMS velocity. So most probable velocity is equal to 0.8166 into RMS velocity. But this formula can be used only when we know the RMS velocity. So what is the relationship between the different types of velocities? So most probable velocity is to average velocity is to RMS velocity. So that is equal to 1 is to 1.128 is equal to 1.224. So this is about the RMS velocity. So with this, I will conclude the session. In the next class, we will discuss about the different topics.